Okay, can you hear me now? Ooh, can you hear me now? Hello, I cannot. Wait, I'm still. Where are you? Where's everybody? Okay. All right, can you hear me now? Woohoo! It's working. Okay, let me turn off a couple things here that are taking resources. Uh, yes, this thing here. Ooh, and I love those emojis, Pixel Car. It's one of my favorite emojis. Where are my notes? I had some notes for today. Uh, okay, yes, I got it. Okay. All right. Good morning, everyone. How is everybody doing? Woo-hoo. Oh, I still need. Wait, give me a sec. I need to kill a couple things. My computer is going to blow up. I need to get a new computer. I bought this one laptop, uh, whose brand or make I'm not going to disclose, but I'm not enjoying it. I'm not very happy about it. And given the times, and given how things are, I think I'm just gonna buy like a nice desktop computer and start streaming from the desktop because it's just gonna be so much better from so many things. Um, I see a lot of familiar faces. Monique Hex, Raymond BVR, Rodolfo, Salvador, Saurabh. Hi, how you doing, sir? Chandra, Pixel Car. Uh, how are you doing? Albert, I think I've seen you on Arasto. How are you guys doing? Good to see everybody here. And welcome, as usual. Very happy to see you here. Very happy that we're spending Saturday morning together. And I'm so excited because today we're going to cover last week's challenge. And I have to say, I was very excited because I'm liking a lot the conversation. Oh, this thing is complaining about data streams. Can you hear me? You can hear me, right? This thing is complaining that it's not getting enough video. Can you see me and can you hear me well? Can you let me know on the chat? Yes to what? Hmm. Uh, yeah, yep, loud and clear. Okay, so YouTube for some reason is complaining that I'm not streaming enough data or something. So just like with audio before, all pixels are clear, pixel car. Just like with audio before, if video becomes sloppy or audio gets cut, just like start blasting the chat, so that I get so that I know that something's going on, please. All right. It's been a very intense week. I see in the chat that it's also been very intense for some of you. So, yeah. Hey, Parastorm, how are you doing? So, yes. I don't know. I think I lost track of what I wanted to say. Um, what did I want to say? Oh, What is the Discord? I want to remind folks that I'm also going to try to pay attention to the live channel on the Discord server, just because we discovered very recently that only I can share links on the chat. But if other people want to share links, then YouTube doesn't allow that. So I'm going to be paying attention, hopefully. I'm going to be paying attention mostly to the chat here, which is here physically for me, right there. But I will also keep an eye on the other one, and I'm going to reshare Discord link for those of you who may want to join the offline conversation that happens over the week. I'm actually super excited because of the challenges that we've been doing and how people have been participating and giving them a try. And the most of what we're going to do today is actually going to solve one of the challenges that I announced last week. The one that was about implementing an optimization routine to find out the best combination of radius and amount of spheres to populate a curve. So we're going to be doing that today. I'm going to show some examples of what people have done on the chat. I'm going to come up with my proposal of how I would do that, so that other people can be informed and can see like a different alternative. But definitely, if you're actually interested in this challenge, make sure you go to the coding challenge channel on the Discord. I can show it here, right? Yes. So on the Discord, we have the coding challenge, and you can see how many people have already tried to solve the problem, and we have like very nice screenshots and animations. I think this is great. I'm actually really excited and enjoying these conversations. It's like the nerd in me could not be any happier about this. So I'm going to propose how I would tackle this problem, and for those of you who have tried, this can inform you and give you like a wider perspective. And for those of you who haven't, then maybe it's just something else that you can learn. I'm going to solve this. I'm also going to record like a really quick geometry gem. It's going to be super simple. It's going to be calculating the length of a polyline, which is literally just a for loop, going over all the segments and adding all those distances. It's just as simple as that. But I want to record that because I think I will be using that gem next week when I solve the other challenge that we have pending, which is the challenge of finding a way to apply Chekhin's algorithm for curve smoothing, for polyline smoothing, but instead of starting from a control polygon, starting from points that we want the curve to interpolate through. So instead of using the control polygon as the input, using points that we want the curve to actually touch, which is a really interesting problem and with very practical uses, such as, for example, robotics, like designing smooth trajectories and smooth paths between target points. It's a really useful one. So I think I might be needing, I still haven't tried yet, but I think I might be needing to compute the length of a polyline. So I just want to have like a function that gives me that. So I may want to record that. And then by the end of the stream today, what we will do is, as usual, we will have like a little bit of Q&A and social. And I will remind everyone about the challenge that we have for next week in case you want to try. So this challenge that I've been talking about Chekhin's algorithm applied to, Chekhin's algorithm applied to a set of points, as opposed to a set of interpolated points, as opposed to the control polygon. Okay, how does that sound? Can you give me some thumbs up or some thumbs down if you don't like it? I also have to edit a lot of the videos from last week. I will need to do that at some point. I'm very grateful. I have a lot of people who are pinging me and offering help with that. I'm actually talking to Arasto right now because he offered to help with video editing, which is, it really relieves a lot of work from my plate and it lets me focus on actually recording content. But yes, so and I see people are joining the Discord right now. Okay, so where do we start? We're gonna start by the beginning, which is usually a good place to start, right? And I'm going to remind everyone about what the challenge was for today. So let me just open right now. let me just open right now. And I'm going to pull up the files from last streaming, and I'm going to drop in here. What am I going to drop? I'm going to drop the pearl necklace. So I'm going to drop this file. And if I'm just going to pop here some curve, whatever. I feel like I always end up drawing the exact same curve, like this kind of gesture. Anyway, so here we saw, last week we implemented two ways of populating a curve with spheres, right? One of them was given the amount of spheres, right? I'm going to do a top view here. Given the amount of spheres, we wanted exactly that amount of spheres on the curve, right? And then if we control the amount, then we can basically do a very simple algorithm where we subdivide the curve into equal length segments, and then we just place the spheres centered there, which is what we have, right? The problem with that process was that because this, for example, this division between this curve, this is equal length to this one, but because this curve is concave, some of the spheres do overlap with each other, right? So that is a problem. And we saw that there was an alternative way, which is like, well, if instead of controlling how many spheres we have, we control the radii of those spheres. And we implement an algorithm where we make sure that each sphere is tangent to the previous one and the next one, then we can implement that as well. But then what happens is that we do end up, because we are controlling the radius of the sphere, we are not guaranteed that the last sphere will end at the end point of the curve. And we will always have some kind of remainder of distance between the last center of the sphere and the end of the curve. So the challenge, and this is a common problem, the problem is that you cannot control all these parameters at the same time. You cannot control how many spheres do you have on the curve and the fact that those spheres are perfectly tangent to each other. You cannot control that. There is not a closed form solution to that problem. There is not one algorithm that can give you that solution, because that solution depends very strongly on the shape of the curve. And it's a very complicated one to solve. So one way to solve these kind of problems is through optimization, through genetic optimization, which is a process which basically is reduced to trying many different values, and then start to find which one of those values gets closer to a very optimal solution, which is the one. So it will be basically saying, for 15 spheres, let's try a lot of different diameters, and let's see which one of those diameter values gives me a value that is as close as possible to having this point be distance 0 to the end curve. Okay? And in Grasshopper, we can do optimizations with Galapagos, right? So the challenge here for this week was take this file and find a way to implement optimization with Galapagos so that I'm going to say it, so that you can control both the fact that you have a controlled amount of spheres on the curve and the fact that all of them are tangent to the neighboring ones, and at the same time fit them with a radius that makes this solution as tight to the end of the curve as possible. Okay? All of those things together, or one way of making them work together, is through optimization, through genetic optimization. So that was the challenge for this week, and I'm very, very happy to show you that a lot of people actually gave it a try, and some of the attempts got closer to the solution. Some of the attempts were either missing one parameter, or the optimization boundaries got totally out of control. And some people did it in native Grasshopper. Some other participants just did it by implementing it by trying it in C# and doing it even trying like continuous execution, so like running a component like multiple times until the component converges to a solution. So I want to call this like manual Galapagos, which I so want to get into at some point. I want to explain to you how to do that, how to write code that does this kind of genetic optimization. But that's a little too advanced for where I think we are right now, or all the knowledge that I'm trying to build. So I'm gonna hold on to that a little bit. But like, I think this is great, and I think Arasto is also doing a really good job at like these kind of screenshots that explain the process, even with annotations here, and these GIFs. How nice is this? Huh? And the optimization pro. Look, it's fitting, it's fitting, it's fitting. Bang! It fit. This is really cool. And I have to say, this kind of material for blog posts, for your personal website, and even maybe for a portfolio, I think this is actually really good material if you want to prove at some point for an application, for employment, whatever, that you actually know what you're doing when it comes to code and when it comes to design, you know? Just throwing that out there, you know? Anyway, for those of you who are interested, please come join the Discord channel. Come to the coding challenges channel, and give it a look. And join the conversation. I have been fairly active on this channel recently. I'm just enjoying the conversation a lot. And then I think after this week, we're going to close up this challenge and we're going to move on to the next one, to Chekhin's algorithm through interpolated points. Okay? Now, what I want to do today is propose how I would tackle this problem. And but I also want to do the other geometry gem, the tiny one, the polyline length. What should I do first? What do you think? Should I do the length of a polyline gem first and then do this? Or should I do this first, and if I have time, then do the polyline? I don't know what to do. I think I'm going to do this one. And then if I have time, I'll do the other one. And if I don't, then we just push it to next week. It's a very simple one anyway. Yeah, I think I'm going to do this one. Any votes? Any strong opinions about what I should be doing right now? I'm going to give you 10 seconds until you hear this. Okay, I do not see very strong opinions against me doing this, so I think that's where we're heading. Okay. So, okay. So then, how are we going to start this? Okay, so I'm going to do this video then. So this is the third video on a series of other two where I solved this problem with C#. Sorry, I solved it with vanilla grasshopper and I solved it with C#. So the third video would be, well, I think there's quorum on doing this one. Okay, so this would be the third video on the series. So I guess, well, I will do as usual. I will record the introduction at the end. But I guess I want to start the video by explaining what are we doing. Sorry, well, I would do that in the introduction, I think. So in the introduction, I would explain that what are we doing. Well, I would explain that the Galapagos thing. So I think I'm going to start by explaining the problem statement. So the fact that we cannot control everything at the same time. We cannot control the amount of spheres, the radius, and the tangency, and the fact that the spheres completely fit into the curve. So, and I'm going to explain that in order to do that, we need optimization. we need an optimization process. And how am I going to do that? I'm going to do that by showing this example and then just moving the radius and explaining that what we're going to do is just basically try a lot of different values for the diameter until we find one that gives us 15 spheres and where the distance, this distance is as close as possible to 0. That is the problem that we're trying to solve. Yes. And then we will use a genetic optimizer, so we will use a Galapagos to try to solve that. I think that sounds good to me. Okay, and I need to add a component here to give me the length of how many elements I have in here. Okay. Okay, so and I'm going to save this as pearl necklace Galapagos. Yes. Okay. So I think we're ready to start, aren't we? I think we're ready to record. Yes. I'm somehow having trouble finding the right words for this. I may have to do a couple of test runs first. But I know you're very patient when I do these things. So, yes. So let's be a little patient on this one because I really want to. And it's also the first Galapagos related video that I'm recording, so I may want to take the extra time to explain some concepts until I record like a series, you know? Yeah, let's think about that. Okay. All right, so, am I good in terms with the, yeah, okay. So let's start. Well, first of all, what I would like to do before we start is to actually make sure that we understand the problem that we're trying to solve, that we understand it very clearly. And I would like to remind you that we're coming from 2 videos ago where we solved the problem of trying to populate a curve with a bunch of spheres. And we did it using vanilla grasshopper, and we did it in 2 different ways. First one was we developed an algorithm where we could control the number of spheres, right? And because we subdivided the curve in an amount of segments where the length, the chord segment between them was equal, then we knew that that like all the spheres did fit perfectly inside of the curve. So the last sphere, the center of the last sphere, was at the end of this curve, right? The problem with this algorithm is that because we are using equal chord length of the curve, when that segment of the curve is very curvy, when it's very concave, we have the problem of spheres overlapping each other. So you see this overlap here and you see this overlap here. So that is not great if we're trying to model something that needs to be physically more accurate, for example, right? So we did develop this other algorithm where what we did was instead we did control the diameter of these spheres, and then what this component does internally is it places one sphere, it computes the intersection, it finds that, and then it places the other sphere and then the next sphere, therefore guaranteeing that all these spheres are perfectly tangent with each sphere is perfectly tangent with its neighbors, right? The problem with this one is that because we are controlling the diameter and we are controlling this perfect tangency, we are not guaranteed first of all, how many spheres do we have? So the smaller the diameter, obviously, the more spheres we have on the curve. And on top of that, we're also not guaranteed that the last sphere, the center of the last sphere, is going to land at the exact end of the curve. Because since this is whatever diameter, then this sphere can end anywhere, basically. So what we're trying to solve here is we're trying to combine more of these constraints. And what I would like to try to do is implement something where we can control the number of spheres, okay? I'm interested in controlling the amount of circles. I'm also interested in the fact that these spheres must be perfectly tangent to each other. And on top of that, I also want to make sure that I minimize this distance and that the last sphere is as close as possible to the end of the curve. All of those things together, all of those constraints together, there is no closed form solution that I can use to reach that solution. And the problem with that is that because that where this sphere lands at the end of the curve depends very strongly on the shape of the curve, the way to compute that algorithmically would be very complex, if it's even possible, which I'm honestly not very sure that it is. Okay, so what we're going to do is we're going to follow an optimization process. We're going to implement an optimization algorithm, which what it basically does is we're going to try a lot of different values of the diameter. So we're going to write an algorithm that is going to basically start throwing a lot of different dices. It's going to start going through all different ranges of values for the diameter, all right? It's going to check first if we have the right amount of spheres, and then it's going to check if the distance between the last sphere and the endpoint of the curve is as close as possible to zero. And the more values we try, the more we will find one of these values for the diameter that will satisfy both the number of spheres that we want and the fact that this last sphere is as close as possible to the end curve. This is what we're going to try, and we're going to try that by using Galapagos, which is a genetic optimizer that is built into Grasshopper. Galapagos will give us the possibility of pointing to what is the parameter that we want to explore. So what is the range of values and the parameter that we want to explore? And then what is the fitness criteria that we want to implement? Fitness criteria is that situation, that value, that result that we want to optimize. And I will explain how that works in a second, okay? So I think we're ready. If that was clear, I think we are ready to get hands-on and to start implementing, to start building towards that implementation, okay? So let's get hands-on. And I forgot to turn off the AC, people. I forgot. I'm not gonna blame it on you, obviously, that's in me. It's really hot in here, but I don't want the background noise. I know I have conversations going on about background noise reduction, etc., but I just don't want to get into that. So I'm cool with just turning it off for the sake of the 3 minutes, the 10 minutes, or whatever the clip. So can you please remind me to turn the AC off? Thank you. All right. How was that for an explanation? Was that clear? Do you think that would be a good entry to developing this algorithm? All right. So what am I going to do now? Okay. So I think the first thing that I need to do is I need to I need to remove all this stuff here because I'm not going to use this. I'm going to use this part here. And then I need to implement first. I need to implement calculating this distance. And then I need to implement calculating this distance. Yeah. And this value, yes. Okay. So that is good, yeah. So I'm going to start by doing that. Okay, so AC is off now. Let's start by the beginning. So what I'm going to do is I'm going to take it off from the gem where I implemented this algorithm in vanilla Grasshopper. And then I'm going to remove all of this because all of this is the algorithm that gave me overlaps, and that's not what I want. I want perfect tangency. So I'm going to start building off from this part here where given the diameter of the sphere, I get all these spheres populated on top of the curve, right? And then because I'm going to be, the thing that I want to optimize is that these spheres, the last one must be as close as possible to the end of the curve. First of all, the one thing that I will need to do is I will need to calculate that distance, the distance between the last element and the end of the curve. I'm not going to do Euclidean distance. Well, let me do Euclidean distance to start with. So the thing that I would do is I would take this list of points. I would take the last point of this list. So I would say, for example, I would say, let me do list item. And then from this list, I'm going to take the last element. And in Grasshopper, you can, if you wrap the list, if you do -1, you can, if you do -1, then basically -1 means the last element starting from the end of the, so if I go here, you can see that the last one is 1324, blah, 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 and this is the one that I have here. So this is the last element on the list, all right? So this is the last point where I divide the curve. Now, I also can take from the curve, there is the endpoints component that gives me, from a curve, it gives me the starting point and the end point, okay? So I could calculate the Euclidean distance, the physical distance between these two. And you know what? I'm actually going to start with that, but I will explain in a second why this is not what I really want to do. We will get there. So this distance is the parameter that I want to optimize. And by optimizing, what I mean is that I want to make sure that when I start trying different diameters for these spheres, this value is as close as possible to 0. That would mean that this sphere will be as close as possible to the end of the curve, right? And I think with this, at a very basic level, I'm already ready to start implementing a basic test, Galapagos test, because I have what I want to optimize. I have the diameter of the spheres, and I also have the fitness criteria. The fitness criteria is the one value that I want to either maximize or minimize. The one value that I want to make as large as possible or as small as possible. And in our case, it's going to be this one, the distance between the center of the last sphere and the last point of the curve. So I'm going to drop here a Galapagos solver. This is here under utils. You can just plug in Galapagos and you can see that there are, because this is an evolutionary solver, everything is phrased in terms of genome, fitness criteria, gene pool, etc., evolution. So, but it's actually much more simple than it sounds. So there are two things that I want to control. First is the genome, and the genome is how Galapagos refers to the value that I want to explore so that I can find an optimal solution for that value. In this case, that's going to be our slider for the diameter. So this is the value that I would like Galapagos to start exploring and finding like a lot of different values and computing those results. And the fitness criteria is going to be this value here, the distance, because what I will want is to tell Galapagos that this distance has to be as small as possible. So whenever Galapagos starts messing with the value of the diameter, Galapagos is going to start reading the value of this distance. And it's going to try to find values for the diameter that make this distance as small as possible. That's the basics of how Galapagos works. So I can double click here right now, and you can see that in the editor, I have a lot of options. I'm not going to get into this at all. I have some links to blog posts by David Rutten, the author of Grasshopper and the author of Galapagos as well. These blog posts are actually really, really nicely explained, and they have really good graphics and really good illustrations. So I really, if you're interested in this topic, I really recommend that you check this out. The only thing that I would like to touch here, which is very important, is the fact that for the fitness, I have two options: maximizing the fitness or minimizing the fitness. In this case, I want to click on minimize because I want this value, the distance, to be as close as possible. If it was the other way around, if I wanted some value to be maximized, then that's what I would click. And then I'm going to click here on solvers. Solvers is the area that gives me access to two different solvers, the evolutionary one and the simulated annealing one. I'm also not going to get into the weeds of how they work or how they're different. I will get to that at some point in the future. And then here is the Start Solver button. Let me first save this file because I believe we may run into performance and crashing issues. So let me do that. And then when we go to Solver, I'm going to try my first run at solving this. So I'm going to, I'm going to double click here. I'm going to put this here. I'm going to put the solvers here, and I'm going to hit Start Solver. And what we're going to see is that Galapagos is going to start messing with the values of the diameter. So you can see that Galapagos right now is trying a lot of different values for the diameter, and is reading here from the distance what distance is getting, right? But you can see that my computer is starting to be not very responsive, and I actually believe that we will probably crash very soon. Is that true? Are we crashing? Crash, 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 crash. Crash, 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 crash. Oh, it is crashing. Poor Galapagos. Oh, it's back. It's back. Well, I'm going to stop this. And you see it's not being very responsive right now. I'm going to stop this because there are a couple things that I would need to change here. Okay? And I will explain why this is not. Oh, bong, it crashed. Oh no. All right, so you see, I'm going to need to restart. Let me restart and I'll get back to you in a second, okay? Okay. Oh, we crashed. Yeah, actually, Arasto, you're right. That's one of the reasons spheres are kind of expensive, but it's actually not a problem with the spheres. It's a problem with the what is it called? With the curve subdivide component, and I will explain that in a second. AC. It's very hot. Okay, oh, not this one. Where are we? This one here. And I'm going to try to do the exact same curve just because, we have that. Okay. All right. So I think we're back, right? And let me do, because I really want an acute angle here to make sure that things are not overlapping, yes, I want something like that. Okay, so I need to explain now that the problem was that the slider can get very small. And when it gets very small, then this computation tends to infinity, basically. So that will be one thing to solve here. Okay. Oh, the AC. Almost. You're not warning me. Okay. Okay, we're back. It didn't hurt. The crashing didn't hurt that much. It's okay. I have a different curve because I didn't save this file, but it's fine. So why did we crash? Well, when we do optimization, optimization can be a fairly computationally expensive process. So if we also have other computationally expensive processes are part of the optimization, then things get very expensive, really. And one of the problems that I was having was that this slider here, the one that we are trying to optimize, I didn't really take good care of making sure that the boundaries, the range of this slider was good for an optimization routine. And what do I mean by that? Right now, the slider, so the value of the diameter could range anywhere from 0 to 10. And look at what happens if Galapagos starts going into values that are on the lower range of this slider. So if the value of the diameter starts getting smaller, you can see that the divide distance component starts getting more expensive. What I have here is is the profiler, which is giving me the computational time that this component takes to compute these values. And this component is particularly expensive just because the way it works is that it does one sphere at a time. It computes the intersection of the one sphere with the curve, and it uses that to generate the center of the next sphere. So it's an iterative process that uses intersections between surfaces and curves, which is a fairly expensive operation. So that's why as I go smaller with the diameter, you can see that the value, the computation that it takes this component to execute, it just increases a lot. And right now it's blocked. You can see it took for this diameter, it took almost a full second to execute, right? And then if I go even smaller, like something, for example, 0.1, I think I may actually crash it again, but it will definitely take exponentially. You see, I'm crashing it again. No. Did we solve? Oh yeah, it solved. It took 10 seconds to compute this operation, and also to render like however many hundreds of spheres there are here. Is also a fairly expensive operation. So Galapagos was crashing because it was requesting very expensive operations due to the range that we had set for this slider. So one way to solve that is to constrain the parameter space that Galapagos can use to explore this particular value. So for example, instead of, and you can see that because we have 0, the closer we get to 0, the exponential growth in computational time, which could even lead to infinity, right? So let's bound that. Let's say that, for example, we're going to have like the minimum value of the diameter is going to be 2, and the maximum value is going to be, there's going to be no bound for that. It's going to be 100. We don't care, right? But as we do that, you see that the minimum boundary now for 2 is something that is, for the scale of our curve, is something that is reasonable. So, so Galapagos is going to have a much easier time now dealing with this. So for example, I think now we are ready to give it another go. So I'm going to double click here, and I'm going to keep minimize here, and I'm going to use the default evolutionary solver, and I'm going to start solving. And you can see that Galapagos now has a much easier time switching between values. It doesn't get stuck on a one value that requires a lot of computation, right? And you can see this is very nice. You can see how Galapagos now is basically exploring, and the interface is really nice for this. It's basically exploring like a lot of different combinations of this value of the diameter, right? And it's trying to find the ones that give us a smaller value for that distance between the last sphere, the center of the last sphere, and the center of the last point. And you can see that right now it's actually reached a very optimal solution, one that is only 0.01 units away from the end of the curve. That's another thing with optimization, with genetic optimization. Very often you don't get an exact result. It's very likely that we're not going to find a result that is going to give us 0 as the distance between them, just because it's we're trying to get an approximation by doing heuristics, is the technical word, by doing a lot of tests and trials and then finding one solution that is optimal. And something very interesting happened here, which is what I want to talk about right now. You can see that if I stop the solver now, the solver found a solution that is even closer to the one that I was showing before, 0.004 units away. So if I zoom in here, they're like so close to each other. Not quite perfect, but good enough. All right, this is how optimization is. It doesn't get perfect, it gets just good enough. But the funny thing is that it found it. I don't know if you remember, but for this solution, for this solution, we had a much larger number of spheres than for the solution that we're seeing right now. And I would venture to say that, and the reason for this is that right now, the way we have set all of these, we are finding a solution where the sphere is as close as possible to the end. But right now, for example, the one that Galapagos converged into, instead of having 15 spheres, it has 18. And if I were to just move this value around and run the optimization again, then it will probably end up converging into another solution that is also very close, that has the last sphere very close to the end, but it's also not 15. You see, for example, it already found one, now it found another one that is a bit closer, now another one that is a little closer. And if I were to stop here, for example, you can see that the result now is like 29 spheres. The problem here is that now we're getting close to what we want, a perfectly fit set of spheres that are tangent to each other and fit the curve very nicely, but we're not optimizing at all for the amount of pearls. We're not anywhere here in the algorithm, we're not specifying that we actually want a control amount of spheres. And so how could we make that happen? Well, we have to understand that because Galapagos is just finding random diameters, among that randomness, whenever it finds a diameter that gives whatever combination of number of spheres, but a good fit on the curve, that's where it converges, right? So what we need to do is we need to somehow, in this process, make sure that the amount of spheres that we want is accounted for in two different ways, as a minimum range, but also as a maximum range. So there are a couple things that I would like to do now then. And the first one is going to be, first of all, to discard all the solutions that give me spheres above the ones that I want. I'm going to discard all the solutions that give me more spheres than the number that I do want as a target. Okay, so let me show you how to do that. AC. Okay, so how are we going to do that? Well, that is going to be just as easy as whenever we calculate all these points here, then we're just going to remove the ones that are over 15. And because we will end up with spheres somewhere here, then that distance will be very long, and the distance will be a lot. So I don't want to do that. That was not very eloquent. Okay, let's just do this. Let's just do it, and let's just do it, and let's just do it. So yes. As you can see right now, when we calculate for a particular diameter, when we calculate the amount of divisions of this curve, we're basically letting Grasshopper, if it gives me more than the divisions, the number of spheres that I want, if it gives me more, I'm just letting it use that many spheres as part of the calculations for fitness. So it's just populating all those points with spheres, and then it's using those for calculations. So that is the first thing that I will need to fix. If when I do divide distance, I get more points than the amount of spheres that I want, then I will need to remove those points from the calculation and then just stick to the first 15 that I want to calculate. So how can I do that? Well, I think it's as easy as taking, for example, all the list of points that I'm getting from this computation, okay? Taking that list of points and splitting the list in two with a split list component, splitting the list in two, and at the index number 15, which is going to give me here at A, is going to give me the first 15 objects, and then in B is going to give me the rest, which I'm just not going to use. So if I plug these 15 objects here, and if I plug them into this list here, then you can see that now I have basically discarded all the points that were beyond my first 15 spheres, and therefore when I calculate the distance, now this value is very large, right? So you can see that now this value, if I make this very small, this value is very large. So Galapagos is going to pick that up very fast, and it's going to start finding values that are closer to. So let me start now the calculation with the minimum radius, the value of 2. So for example, here I'm going to now run the calculation, and I'm going to run the solver, and let's see what happens. I start solving, and then you can see that immediately it finds a larger value, right? And it found an optimal solution with 2 spheres. Now with 6 spheres. And if we let it run a little longer, it will probably find some other more fit solution. Oh, again with 2 spheres. I mean, this is true. 2 spheres are fitting perfectly now on the curve. But you see, so what we've done is we have managed to find a solution that is under the amount of spheres. Okay, but so we have been able to penalize the fitness criteria if it gave me a solution that had way too many spheres on the curve, right? I find it really funny that it has found like a very, very nice solution for 2 spheres right now. So what we would need to do now is we would need to find a way to penalize also the fitness criteria if it is giving me too few spheres. If it gives me a solution like this one, for example, where if it gives me a solution where we only have 2 spheres, I need to be able to somehow artificially increase this value a lot so that Galapagos thinks that this is not an optimal solution. Okay, and this relates to the problem that I was saying before, and the fact that I'm not very happy with the fitness criteria being the Euclidean distance between the center of the last sphere and the end of the curve. Because think about this. It could happen that if this is what I'm using, it could happen that if I take this curve and I take this point here and I put it somewhere very, very close on top of the curve, it could happen that as I am, for example, here, right? It could happen that Galapagos could find a solution where it could populate all of this with spheres all the way until here without actually closing the loop, just because the Euclidean distance at some point here is very small. Let's try this. Let's hope we get some luck and we find something like that. You see? We did. So we are now converging to a solution where the last point is actually very close to the end point of the curve, but not in the way that we want, not fulfilling all the curve. So for me, Euclidean distance is not a great measure of what I want to do. So how can we change this? What I would propose to do is, instead of using Euclidean distance, what I would like to use is I would like to use the domain of the curve. What does that mean? If you've seen my other videos, you know that curves have this thing called the internal domain. So for example, I'm going to say domain here, I'm going to deconstruct the domain, and if I plug in this curve here, you can see that the curve starts at 0 and ends at 64. Domains have this, curves have this thing called the domain, which is basically a measure of the internal length of the curve. It's not exactly length in terms of world units. It's more of it's a concept that is not very straightforward, but it's basically how the internal points of the curve are distributed along that curve. But the main takeaway here is that we can measure where we are along a curve, both in the length of the curve, in the length of the chord of that length, but also we can measure as in which parameter are we along the curve. So the parameter being that value between 0 and, in this case for this curve, 64.41, which again, this is not the length of the curve, this is the domain range of that curve. So if we say I want a value whose parameter is on this curve at, for example, 10, then it will probably give me a point somewhere around here, okay? And we also know that this point here, the end point of the curve, is at the parameter 64.41, whatever, of this curve. Which means that I can measure, for points, I can measure where I am along a curve by finding the parameter of that point on top of that curve and computing how far along that curve I am, right? So how can I do that? If I take this point here, the last point that the last point of my subdivisions, what I can do is I can say, can you find what is the closest point for this point to the curve? All right, and that point is probably going to be, because that point was on the curve, is going to be the exact same point, right? But this component also gives me this other thing called t, which is the parameter on the curve domain of this closest point. You can see that right now is 38, which is kind of halfway between 0 and 64. And if I start cranking this up, and if I try to bring it all the way very close to the endpoint, you can see that this parameter right now is going to be 62 point something, which is very, very close to 64. So I think using the parameter of the center of the last sphere and the parameter of the endpoint of the curve is a much better way of finding a fitness criteria for this too. And what I'm going to do is I'm going to subtract this, and I'm going to say the value of, if I subtract the value of the parameter at the end of the curve, okay, with the value of the parameter of the last point of the sphere, this value right now is like 1.4 something something. If I make this varies, if I reduce the radius, you can see that this value is much larger. But if I crank this up so that this is closer, this value becomes much smaller. So this is a really good candidate now for optimization. We're going to optimize the difference in parameter at the difference in parameter between the center of the last sphere and the endpoint. And proof of that is going to be that if I now do the same thing as I did before, if I put this point on top of the curve and I move this all the way back to 0, then if I now try to optimize, I don't think this is going to get stuck on a solution that has spheres ending up here. You can see that it got stuck on these like 7 spheres, but it's pushing the spheres as much as possible to the end of the curve. It's not getting stuck here. So I think curve domain is a better approach. And so we are now on a better position, but we still have the problem that we are not going to find a solution that gives us more spheres than the ones that we want. But we may find a solution like we just did right now that is giving us less spheres than the ones that we want. So what we need to do now is we need to find a way to penalize the fitness criteria if the spheres are less than the ones that we are targeting. And I think for that, I'm going to have to draw a diagram to explain that concept. So let me get into the whiteboard. All right. How is this going? Is this clear? Am I making things fuzzy? What do you got? What do you think so far? Okay. I need sketchbook. Okay. So, oh yes, drawing here. I'm going to draw this curve here. Okay. Now I'm going to draw a curve like this, and I'm going to draw points like oops. Another layer, so points, 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 and this one is going to end up here, for example. And then what I would like to explain is that what I would like to explain is that if we stay too short, then it's easy. But if we yes, so if imagine that we extended this curve like this, for example, and then we started so, and then if the parameter here is 0, oh, I'm not going to use green. If the parameter here is 0 and the parameter here is 64 point something something something, right? So what I can do is I can artificially come up with a larger value for this parameter. So that, for example, this can become, for example, I don't know, 91 point something something something. And let me try to explain this, and if I don't make a good job about it, then I can redraw the diagram. Yeah, because I'm not sure what I'm going with this. I know it's in my head, but as with many things, explaining it sometimes it's just so much more complicated than actually doing it. So, and you're gonna see that when we do it, it's just like multiplying two numbers. But I need to get the concepts clear and across. Okay, let's do this. So what we want to do is we want to find a way to penalize artificially the fitness criteria so that whenever we have fewer spheres that we want, to let the fitness criteria know that that is the case by artificially changing the value of you see, and starting over again. That was not right. What do I want to say? Penalize. Yeah. Mm-hmm. Yeah, I may need to draw some. Okay, yeah, I may need to draw while I'm explaining this. Okay. Um, mhm. Okay, so let's imagine we have our curve, all right? And then that we apply the subdivision algorithm, and then we end up with some points on top of the curve. And then we know that the domain of the curve goes from 0 to 64, for example, or whatever in this case. So we know that what we're doing right now is we're calculating the distance between this domain here and the last domain of the last point. So this might be, for example, 1.3, blah, 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 whatever, in domain space, not the Euclidean distance, right? Remember the domain in parameter space. The problem with our algorithm is that we are computing this parameter distance no matter how many points we have here, whether if those are 2, 3, 15, or whatever. What it's just the result of the diameter of the spheres. We fit however many spheres, and then we calculate that. So Galapagos is not making any difference whether if here we have 3, 10, or any amount. So what we need to do is we need to somehow make sure that this value is also representing the fact that we may have more or less spheres than what we want. And what we can do is we're going to do like a trick. And the trick that we're going to do is that we're going to imagine that we were to continue this curve and to actually fit the exact number of spheres that we wanted. Okay? What does that mean? Imagine that here we have, for example, 7 or 10 spheres, but we actually wanted 15. So we can imagine, for example, that we extended the curve and that we actually extended the algorithm and we kept populating this curve with however many spheres. The idea would be that the last sphere will end up somewhere in the parameter space with a value that is actually much larger than what the domain of the curve can hold. So if we were able to find out what this number is and then use this distance as the fitness criteria, this would be like 23 point something something something, that would mean that because that number is so large, then Galapagos will try to reduce this number, therefore starting to fit all those 15 spheres closer and smaller inside of the domain of the curve. All right? So, and this would only happen when we have less spheres here than the amount that we have. When we have, yeah, you understood that. Now, the problem is that we cannot really extend the curve, and we cannot really populate that extension with more points. If we were to do that, it would be a very expensive operation, and it doesn't really make sense. So what we want is to actually find a way to artificially cheat Galapagos and feed Galapagos a value of the domain of the last point here that is not exactly the one of the real point that we have found, the real point being one that is less than the amount of spheres, but one that has been artificially increased to reflect this imaginary notion of us extending this subdivision beyond the boundary of the domain of the curve. All right? And how can we do that? We can actually do that with a very simple numerical rule. Because if we say, for example, let's say that the let's say that for let's say that the domain of the curve goes all the way to 64. All right, and let's say that for a particular radius, so for example, for the radius of 3, what we got was 7. We got 7 spheres here inside of the domain, right? What that means is that proportionally, more or less, we can think that if we had gotten a radius that had given, for the same radius, if we could subdivide like a longer curve and get actually 15 points, the ones that we want, more or less, we can estimate that the domain at which we would end would probably be roughly double what we have right now. Because this is 64 and 7 is roughly half 14, we can estimate that more or less we would end at that, for that particular radius, we would end at a domain that would be at 120, for example. If we do that estimation, then Galapagos would understand that the radius of 3 is too large because it's giving it a value of the domain for 120, and then when you subtract that from 64, then it gives it like a really large number, and then it's going to try to reduce that number. Okay? So, what I'm trying to say with this is that we can perform a proportional rule where we say, given the amount of spheres that the algorithm is giving me for a particular radius, I can estimate for the total amount that I want, I can estimate where the domain of the last point would land in an imaginary curve that will be extending infinitely. And if I estimate that number, and that is the value that I use for calculations for fitness, then Galapagos will understand that for that particular radius, the last imaginary point would end up too far away and then would start constraining the radius, making it smaller and therefore fitting that imaginary sphere closer to the end of the actual curve. I hope this idea was clear because it was very tedious to explain, but you're going to see how numerically actually on Grasshopper and Galapagos is super easy to implement. So let's give it a try and see how this looks actually as an implementation. Woohoo! All right, let me save this. Let me go back to the drawing board. How was that? What do you think? Well, let's wait. Let me show you how it's done, and perhaps that actually helps, because otherwise, I think it's a little too theoretical. Yes. So we are here. I'm going to go back to 0. Yeah. Okay. Okay. So I'm going to. All right. Okay, so back here, I have chosen manually a diameter that is giving me 7 spheres, okay, which we know that is roughly roughly half the amount that we actually want, because we want 15, right? So we can make a very simple proportional rule and say, I'm going to divide the number 15 by the number of spheres that we actually have. And the result of that is going to be like 2 point something, 2.1, because 15 is a bit bigger than 2 times 7, right? And if I now take the parameter of the last point, so this is 63 3 point something something, and if you remember, the curve ends at 64, blah, blah, blah. If I take that number and I multiply it by, if I multiply that number of the parameter by this proportional rule, what you can see is that what I'm ending up with is with this value of the domain 136, which is an estimation of where that an imaginary sphere, the 15th sphere, would land on a curve that would extend here, blah, 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 infinitely, if we stuck to this diameter. It's not exact because we don't really have that curve. It's just an estimation, right? But because we have this really large number now, this really large number is an estimation of where that sphere will end up with, and because it's so large, then you can see that it's giving me a very large number here, which I think is a good indication for Galapagos to understand that this is not going well, that this diameter here is too big and that it needs to reduce it so that this value becomes as close as 0 as possible. So this is what I meant with, it's much more complicated to explain than to actually, because it's literally just one division and one multiplication. But let's run Galapagos now and see if this is going to work, which is not, and actually let me save things around in case it crashes. It's not going to work, but I think it's, so see what's going to happen. Galapagos is going to start solving, but it's going to end up converging always into a value that is close to 2 spheres. And wait, how is that possible? Let me wrap again. Let me go back to this minimum value. If I try that again, and I try solving again, it's also going to start and explode and become, and also converge into a solution that is just 2 spheres. It's the least amount of spheres as possible. Why is that? Because we have skipped something, a concept that is very important. And remember when I said that the Galapagos is trying to optimize for minimizing a fitness criteria? So what we have here is that because we have artificially increased the domain where the last point ends, this value of this abstraction can actually be negative. And what happens is that negative is actually a more minimal value than 0. So Galapagos tries to go as far down in the negative space as possible, because negative is less than 0. So it's more minimized in a way, right? So that's why Galapagos is always trying to get the most negative value here, which ends up being the one that has this imaginary sphere as far as possible on space, which ends up with us just having 2 spheres here on the real curve, right? So how can we solve that? Well, then it's actually very easy. So we can just calculate, instead of leaving this value signed so that it fluctuates between very positive and very negative, we can calculate the absolute value so that minus 405 becomes positive 405, which is a really bad value for the fitness, which Galapagos will try to reduce to the value of 0, which is as small as you can go for an absolute value. And I don't want to disclose anything, but as we click here and we click on the optimizer and we start solving, you can see that we have now converged to a solution that is a pretty good solution. It's at 0.07 parameter space units from the end of the curve. And if I stop this, I can probably see that it's got 15 spheres, and I can zoom in and see that this value is very close. If I now start from another value that is probably like very large, like 1 sphere, I can also see that if I start the optimization process and I start trying to solve, the solver is going to reduce this number very fast. And I believe we are probably now at 15. No, we are not at 15 yet. We are at 15 now, I believe, yes. And we are getting closer here. I can't zoom in here. I can only zoom. Oh yeah, I can zoom. I can zoom here. Yes. And if I stop, you can see that we are at 15, and we are also pretty close. I could leave this running a little longer, and we will probably find a value that is closer to the end. But I think with this, we have basically solved everything. Let me see. Yep, it did find a better value, or now a much better value even. So if I stop and I press OK, you can see that we're all super, super close. And again, with optimization, there's a compromise between computation and a fitness criteria, and we know that very likely we will not hit a perfect solution, we will hit a very optimal one, but not one that gives us 0 as the remaining parameter distance here for the curve. Okay, so I think with that, this is everything that I wanted to explain today. I hope that by purposefully having run into all the possible problems that we could run and all the possible things that could go wrong while we implement this, I hope to have made a good point first at explaining conceptually how genetic optimization works, but also at making sure that we understand the concepts underlying them and how we need to do some numerical manipulation to make sure that the optimization, the solving process, always stays within the boundaries, but also it gives us solutions that are constrained in the parameter that we're trying to solve. This was the first video that I have recorded in this channel about optimization and with Galapagos. So maybe that's why I took a little longer to explain certain stuff, but hopefully I will at some point record a series of a playlist or something with like more in-depth, like what is Galapagos, what are the options, what are the different solvers, and like a series of different examples that explain how different things affect different, basically an optimization playlist with a lot of, where I explain more in detail on the underlying concepts. In the meantime, I hope you liked this video. If you did, please click subscribe and hit the bell button and like the video and all those things. It just helps me keep the culture growing. And until then, thank you very much for being here. Check the other videos on the channel and see you soon. All right, and now we need to record introduction. Please not forget about this, okay? All right. How was that? Was it clear? Was it interesting? I don't think the problem itself is very interesting, but I think it was a really good exercise to explain a lot of the things that I think can go wrong with optimization and when things don't seem to converge, you know? But I think, yes, I think that was a good. So, so let me, because I hate this spaghetti. So let me put a little bit of order in here before I show this. Implementation was easier than it sounded. It was, Monique. Thank you. But yeah, it's like once you know what can go wrong and you have a clear sense, it's actually very easy and the numbers are very straightforward. It's I think it's the underlying concept that they need some explanation. That's why it took us a little longer. So here I'm going to say compute fitness, compute artificial parameter distance to from last center to end of curve. Not artificial, virtual. Yeah, I like that better. Yes. And deconstruct the domain. I will probably want to just move this somewhere here. Yes. And add to group. Yep. And then the diameter, I'm going to move it here. Up. I'm going to add it to the group. Okay, so here, here, and I'm actually going to move this all the way to the beginning. I'm going to move it up. I'm going to remove this from the group. I'm going up. I'm going to put it here. I'm going to change the wire to hidden. Sphere count. Number of spheres. Okay, and I think we don't need all of this. We don't need to show all of this one for the introduction. I think we just want to show the thing. We just want to run, and I may want to have room here for the optimizer. So if I double click here and I fit it here, it looks good, and it looks like, yeah, I think this is probably a good screen grab kind of situation. Yes. All right. Okay, so let me record an introduction. Oh, my head is on the way. All right, so let's get this somewhere over here. And okay, that looks a little better probably, right? Okay. Okay, and let's do an intro. I have a headache. Oh, yeah, I don't think I'm recording the other gem. I'm sorry. Okay. Hi, and this is Jose Luis, and I'm. I couldn't even get through that. Okay, starting over again. Hi, this is Jose Luis, and welcome to another geometry gem. This one is a continuation of the two previous ones where we were solving the problem of fitting a bunch of spheres along a curve, right? But for this one, it's going to be a little special because what I'm going to try to do here is I'm going to try to pack as many constraints in this algorithm as possible. Those constraints being controlling the amount of spheres that I'm going to fit the curve with. I'm going to constrain them so that they're perfectly tangent to each other, so that there are no overlaps. And on top of that, I want to be able to make sure that the radius of the sphere is enough so that these spheres fit all along the curve as perfectly as possible with the least amount of remaining distance here at the end. The problem with all these constraints is that there are so many that there is no closed form. There is no one deterministic algorithm that I can use to pack all these constraints together. So what we're going to do is I'm going to be using Galapagos, which is a genetic evolutionary solver inside of Grasshopper. I'm going to use it to basically go over all the possible values of the diameter and find the one that is the most optimized to satisfy all these constraints that I just explained. And I'm going to show it working here, so you can see that right now what I do have, you can see that right now Galapagos is trying to optimize and is going through trying like many different iterations of the diameter, and it's trying to find one where it gives me 15 spheres, and it's trying to get this distance as small as possible. And you can see that over time, the more it tries, is converging to a better solution here, one that is giving me a very small distance here by the end. So I think this is a really interesting exercise to do because it involves optimization, and it involves thinking about what's called a fitness criteria. So how do we generate a value that we use for the solver to optimize, to either minimize or to maximize? I'm going to explain. I'm going to pick it up where I left on the 2 gems ago, where I implemented these algorithms in vanilla Grasshopper. I'm going to pick it up from them, and because this is also the first optimization slash Galapagos video that I'm recording, I'm going to be perhaps a bit slower, and I'm going to stop in all the stages of the process and explain them very carefully, because I want to make sure that we understand everything that is happening. Hopefully at some point in the future, if you're watching this from the future, there will be an optimization playlist at some point, but it doesn't exist right now. So I'm using this gem to almost as an excuse to do my first introduction to genetic optimization. Okay, it's going to be a super interesting one if you're interested in optimization, and it's going to be a fairly easy one to implement. So stay with me, and let's get hands-on. Woohoo! Oh, all right. I think that's it. Air conditioning. All right, I'm going to save this. I'm also going to save this. Why not? Uh, okay. And I think that's it for today. I have a headache. I cannot keep recording. I'm sorry. Oh, well, I'm going to go drink some water, and then I'm going to come back, and I'm going to explain again what the challenge for next live stream is going to be. Um, the challenge is going to be, again, it's going to be a version of the check-ins algorithm that we did a couple weeks ago, but I'm also going to do a little bit of Q&A and social. So if you have questions, if you want to chat about anything, start thinking about them and start writing in the chat. I'm going to be back in 1 minute. I'm just going to drink a little bit of water. I'll be right back. Okay, I am back. Okay, alright. So, let me close a couple things here. Uh, let me open. Save as. What am I looking for? I'm looking for check-ins algorithm. I was here. Yes. Okay. Uh, 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 um, and then the layers are. Yeah. Let's go back to this screen here. Okay. Where's the thing here? All right. Okay, so just a reminder for the challenge for next week is remember how we did check-ins algorithm. Can you hear me? Yes. Remember how we did check-ins algorithm, where we could start from a control polygon and we could end up somewhere. We could end up somewhere creating like a smooth curve that touched that control polygon at the centers, right? The challenge for this week is I would like for us to try to implement a version of check-ins algorithm where we end up with the same result, but the start of the calculation, the input, is not the control polygon, but it's instead the points. So actually, let me turn this off. Actually, I'm going to explain this way. And I'm going to add another layer here, which is going to be this one here. Okay, and I would like, yes. So the point is going to be, if I start, the goal is to be, I want to start with a series of points, and then I want to end up with a smooth curve with a smooth polyline that passes through all of those points. And I would like for you to try to use Chaikin's algorithm to do this. Now, the problem with this is that what we're actually trying to do behind the scenes is, starting from these points, we're actually going to try to reconstruct which control polygon is the control polygon that would correspond to those points, so that the resulting curve that I create by applying Chaikin's algorithm to that control polygon is the one that ends up passing through those points. This is an extension of the work that we did for Chaikin's algorithm. It's a very interesting one because it has many more practical applications than starting from a control polygon. A control polygon is somehow an abstract thing, whereas the interpolation curves, the interpolated points, the points through which the curve actually goes through, they're typically much more interesting, because if you're doing path planning for robotics, for example, you want the robot to actually traverse through those points. So that's typically a more interesting one. I would like to say, though, that having the control points, and so having the interpolated points and finding the control polygon, it's an unconstrained problem, which means that there are infinite solutions to that problem. This one that you're seeing here is one, but this other one, this other one, for example, this one, this one, this one, and this one could also be another control polygon. Even this one, this one, this one, and this one could also be another control polygon. This one, this one, this one, this one, and this one could also be another control polygon. There are infinite solutions to this problem. Okay, so I have two suggestions. One, if you want the easy life, then in order to constrain this problem so that it has a closed form solution, write an algorithm where you have the input points, the interpolated points, but you also have this point, the very first point on the control polygon. Think of that as somehow imagine that you had these points, and you had like a tangency vector of sorts, right? Where that tangent vector ends is kind of the start of this curve that you have here, right? That's if you want the easy life. If you want the more fun, deeper life, then try to come up with a solution, probably through optimization, through genetics, through whatever, that gives you a control polygon from the infinite solutions that has some kind of optimization built into it. For example, one solution that I can think of is a control polygon where the overall distance, where the overall length of this polyline is as small as possible. That will probably give you a control polygon that is kind of good fit to those points. Maybe you can find another one where like maybe you take a look at these angles, and then you maybe want to do something where you minimize the average of those angles or you maximize that average. I don't know, but think about this problem as a problem that needs some kind of additional constraining. So whether if that is adding this point to the calculations, or going through several iterations of Galapagos, or like a while loop or whatever, and trying many different polygons and keeping the one that has, I don't know, the shortest overall length or the shortest average of angles or whatever, that's absolutely up to you. Okay, you can choose whatever kind of approach to that, but I think this is actually a really cool exercise, and if we get this together, then this could be like a really nice path planning algorithm, for example, in three-dimensional space, you know? On top of that, to this polygon, we could then apply the Douglas-Pecker simplification, you know, so that we have like less points over it. We can do a lot of things here. It's going to be cool. So I would like to propose that as the challenge for next week, and I believe it will not be next week. I believe it will be in 2 weeks, because next week I'm going to take it off. So I don't think I will be streaming next weekend. Okay. So, but yeah, and I'm very excited about this algorithm actually. So I'm gonna leave that up to you. You give it a try, and then if you, as usual, please, where am I? Where is my mouse? Yes, feel free to join the conversation here on Discord. We have a channel. It's called the Coding Challenges, and this is where we keep the conversation going. This is where people post their solutions. We talk about them. We get fancy with emojis. It's very cool. I'm actually enjoying this process a lot. So feel free to join here and post your solutions here on the Discord. I'm going to share the link to the Discord again. Invite people. I'm going to share it here on the chat again. And yes, and I'll see you, and I will try to solve this problem myself next time we meet, which I believe will be in 2 weeks. Okay. And with that, I'm done. Do we have any questions, conversation, social, anything you would like to talk about? Oh, I was very thirsty. Oh. Okay, well, if I don't see Chandra talk to now, I'm not sure what you mean by that. Um, uh, okay, let me check a couple things here. Okay, all right. So after COVID-19, upcoming architects, uh, life and opportunity. I think, I think, I think I think we all have to make the best out of this situation and just try to find opportunities to adapt the times that we're living in to the things that we want to do and the life that we're living. Um, I think I said this before at some point. Like I had actually been meaning to start this project, the live streaming and recording videos, whatever. I had been meaning to do it for a very long time. I'm talking years, but I always had some kind of excuse, like, oh, I had a job, oh, like I'm finishing my doctorate, or blah blah blah, whatever. And I realized that when all this thing hit the fan, I realized that it was just excuses that I just hadn't really decided to do it. And now that I was locked in my apartment and I had a little bit of more free time, I was like, I think this is the time to start this project. So for me, COVID-19 somehow was a little bit of a trigger to start this project. And for me, it was also a way of like trying to make the best out of the situation that we have. And I have to say, I'm enjoying this process a lot. I'm learning a lot from you. I'm learning a lot about myself and teaching and explaining concepts. And I think this is going to be really helpful for me as a professional educator as well. And I hope to. No, I'm not. I don't hope to. I am going to continue doing this for as much as I can, COVID or no COVID. I don't care. You know. So yep. So I think COVID and architecture, everybody has to do whatever you can. Another good thing about the situation is that a lot of companies and a lot of people are understanding that working remotely and collaborating with remote collaborators is much easier and much more feasible than we used to think. So I very much encourage people now to reach out for like remote opportunities, work from home, that those kind of things that before were a little more difficult to get through just because we didn't have such a strong culture of doing that, you know? So COVID is what it is, and but it's always up to us in general. And this is not just COVID. This is about any bad opportunity or any bad situation that we go through. We just have to like be optimistic and try to make the best out of what we can. When life gives you lemons, I love lemonade. I like it. I like it a lot. Um, so Grasshopper was invented in 2007. Why did it see a bigger popularity just now? Are we experiencing a new style? What do you mean by right now? GH tutorials. Right now, so I don't think it's exploding right now. For me, my perception is that Grasshopper exploded as a concept in around 2000, somewhere in between 2010 and 2015. I think that was like the huge ramp up of like people under, getting to know Grasshopper, understanding computation as a possibility, implementing it in their workflows, and and actually now in school, what I teach here at Harvard, I see most of the students now. Nobody is fascinated anymore about computation as a thing. It's not a new thing. Everybody understands that it's another one of the things that are out there and can help you become a better designer. Just as we used to think of theory, of reading books, of like visiting buildings, like all those things. Now it is understood that Grasshopper is as valid as a tool as Rhino, as Photoshop, as Illustrator, as AutoCAD, as like any other digital tool. With the additional with the additional advantage of like allowing you all these parametric possibilities and computational thinking, which is very good for automating a lot of processes. So I also think that the concept of a new style, even in Patrick Schumacher's parametricist discourse, etc., I think we're a little over that. I think the fancy for form for the sake of form, I think we have matured a little bit beyond that. I don't think now you can get away in a competition with just like some fancy geometry just for the sake of it. I think we're a little beyond that, and I think now we are experiencing a more mature understanding and approach to these things, and at least that's my perception from my educational role and from my peers that are in industry and are trying to make a living out of these things, right? Yeah. So Jay, are there different types of optimization algorithms? Yes, there's a lot of different ones and a lot of different techniques. There is brute force. There is quasi Monte Carlo. There is evolutionary solvers. There's simulated annealing. There's a lot of it's a whole different world. So I will hopefully at some point make a playlist where I will explain some of those concepts, both using bare bones implementations in C#, but also using Galapagos as an interface to implement them. But what's interesting is that most of them, you can get away without knowing how they work internally. It's almost like machine learning and neural networks. You can get away you can get very far without actually knowing how the neural network works internally, so long as you understand what the neural network does and at a high level, and which parameters do you need to control in order to make it work properly. Same with optimization. And actually, machine learning it's just optimization. It's another way of optimization. So yeah. People seem to be more interested in it and the opportunities that it offers on the job market. That's a good point. With being a more mature, yeah. All professors are reliable analysis the future. Yeah, it's also a very marketable skill, honestly. So if you know computation, if you know how to write code, if you know how to use Grasshopper, then you will find a very particular space in very particular offices who need these things. There is also a growing awareness that computation is needed to optimize processes and make them more efficiently in architectural practices. So if you want to be that person, if you enjoy that person, there are a lot of growing opportunities now in that space, just as there used to be for people who were good at doing 3D renderings or people who were good at doing Photoshop and collages. If that's what you want to do, you want to spend your life doing Photoshop and you're happy with that, that's great. I think as a skill in itself, it's also very marketable. And it's probably above some of the other more classic design skills, just because it involves a lot of technical knowledge, which sometimes is a bit harder to get. But hopefully, because you're here and you're watching these videos, you're getting some of that for free. I've seen in your tutorials that most of the Grasshopper coding is in C#. Do you know any resources which focuses on Grasshopper coding in Python? I do not. I'm sorry. No. Wait. I'm lying. I do know resources. There's a book. There's the Grasshopper Python. There's Python scripting for Grasshopper. No. Isn't that a resource? What am I? Python scripting for Rhino. What is Rhino Python? Rhino guys. This one. This one. Rhino Python 101. I think this is specifically for Rhino. Is not for, but I think it does have a chapter on Grasshopper. And So you may want to check this out. It's also free. Um, um, so I think you may want to try this out. Just go to here to Rhino Python guides. You're gonna find a lot of documentation here, Raimon. And thanks for the kind words. Chandra, APA policy. I'm not sure what APA policy is. Sorry. Uh, that's a whole lot of words I can't pronounce. I will have to look those up. Just definitely interested in the series. I can write them down. Brute force, quasi Monte Carlo, simulated annealing. Yeah, they sound cool, huh? These are the kind of things that we need to learn also to impress clients. They're very fancy words. What is the line of one draws between optimization and machine learning, and can we use them interchangeably? So actually, for a data scientist, Galapagos is no different at all from from using regression for training a machine learning neural network. It's just that, yeah, it's like for data scientists, the processes are the exact same ones. At the end of the day, it's all math and it's all statistics. So whether if Galapagos is a more UI-based optimizer, that's one thing, and whether if TensorFlow is more of geared towards machine learning using GPUs, etc., it's a different story. But the underlying math is very, very similar. So theoretically, you could use them interchangeably, but you would need to know how to do that and how to write that code from scratch. So that's probably like that's probably the curve, the learning curve that you will need to jump. Wow, and the headache is hitting real hard right now. Okay, so I hope to have answered some questions, but I think the headache is kicking in pretty bad, so I think we're going to call it a day, if you don't mind, okay? Thank you very much for being here, as usual. Hope to see more of you. I hope you try the challenge. It's going to be fun. You can also, I believe you can also try it in vanilla Grasshopper, so long as you have some kind of like for loop plugin like Hoopsnake or Anemone or one of those. But if you want to try C#, then better for you. You will probably learn more from that. Thank you very much, everyone. It was a pleasure, and see you next time, next live stream. Bye bye.